Okay, so let me do an example of iterated double integrals so that you see in practice how they're going to be computed. As I mentioned, they're really computed in the same way in which we were doing like partial derivatives. Namely, you would just do like an ordinary derivative by treating one of the variables as a constant. Here we'll do the same. You would just do like ordinary definite integrals by treating the other variable as a constant. Okay, so just as a reminder of what I said in the previous video, the idea is that let's view this in two different ways. So you had a function c of f of x comma y, and there are 2 points of view. So one is the graph point of view, or the domain point of view, and the other is the graph viewpoint. Okay, so in the domain viewpoint, you only care about the values, the place where you are going to do the integral. Okay, so say here is xy. So let's say that the integral is going to take place on a rectangle, which is 1, 2, 1, 3. So this rectangle is our region of integration. On the other hand, on the graph viewpoint, you not only draw the domain of the function, but you also draw an axis for the values the function is taking. So here, you would have the same rectangle, but now looked a bit differently. Okay, and the point of doing this is that now you can look at the graph as a surface above the rectangle. So that again, the volume between the graph well, this is not meant to be a cube. It's just it looks very similar to a cube because my surface is quite flat. But imagine the volume between this region and the floor is a double integral we're trying to compute. So this is what we're trying to do is representing two different ways this quantity. Okay, and now in practice, what I said last time is that you can really just compute this in two different ways. So that's the concept of Fubini's theorem. So you can either slice the domain using vertical arrows or slice the domain using horizontal arrows or segments. And so the pink ones, right, had a fixed value of x. So the pink ones look here like this, right, because here x is fixed. The orange ones have a fixed value of y. Maybe I should have used a different color for orange for these horizontal ones. And the different segments will slice up this region in different ways. And what we were saying before is that it doesn't matter which slicing procedure you use. So let's begin with the slicing of the region where you're using vertical arrows. And to make things more concrete, let's do this in an example. So let's say you want to find So you want to find the double integral of this function. So where the region R of integration is, let's put it here. from 0 to 2 and from 0 to 1. So again, you have to imagine that this gives you a graph above this rectangle, and you're trying to compute the volume between the graph and the rectangle. But I just want to emphasize this point of view because once I do an example of a triple integral, we won't be able to draw this. So it's better to just think about it in this way. Okay? So let's try to do first the slicing with vertical segments. So do vertical segments first. And that's called the order dy dx. So again, what's the point? Let me draw the rectangle here one more time. What I'm trying to say is that I'm trying to decompose this region into vertical segments, right? Again, the region goes from 0 to 2 and from 0 to 1. Now, dA, the thing that you have to observe is that dA, this is always dy dx or dx dy. So the choice that you're making, there are only two possible choices you can make, and depending on which choice you make, that's how you land in a particular order of integration. Okay? So here I'm taking the order dy dx, which means that I want to take this as my notion of dA. And so if I do that, what I'm trying to find really is the same function. The function never changes. But now you're going to replace the A with dy dx. Okay? And again, how is it that you're supposed to read this expression? So you read it from the inside to the outside. So imagine that you're moving from the origin here towards the endpoints. And so, as you move away from the origin, the first variable that you meet is dy. So what that means is that you're going to integrate first with respect to y. Okay? And so since you're integrating with respect to y, the bounds that you have to put here are the bounds for y. And so y can go from 0 to 1. Right? Here's x. Here's y. So you see when you use these vertical arrows, what you're saying is that the values for y are from 0 to 1. Okay? And then finally, so x was fixed, right? That's the point here. So first, you're integrating with respect to y, so x is like a constant, which is this constant here because you're fixing it. And then you just let this x change, right? And when as x changes, it changes from between 0 and 2. So those are the bounds for x. Now, if you and again, I'll do this again with the other order of integration. But the point is that if you know how to set up the integral, then really you are not doing anything you didn't know before, because this is like a partial integral. So let's just work out what I mean by that. So what should the integral from 0 to 2 of the integral from 0 to 1 of 4 minus x minus y dy dx be? Well, again, what this is saying is that in this first integral, x is treated as a constant, right? So again, think of this as a partial integral. So x is constant. So how would you integrate this? Well, the integral of 4 with respect to y, that's 4y. The integral of x with respect to y, well, x is again is like a number. It's not really different from 4 in this context. So this should be minus xy. And now the integral of y with respect to y, that's really minus y squared over 2. Okay, and this is being evaluated from y equals 1 to y equals 0. And notice that the remaining integral is still waiting for you to finish doing this first. So let me just write it again. And when you evaluate at 1, so you get the integral from 0 to 2. When you evaluate at 1, you get 4 minus x minus 1/2. Right? And when you evaluate at y equals 0, you don't get anything. You get 0, 0, 0. And so, now notice that this is an expression on x. This is like the a of x function that I referred to in the previous video. And so now you just integrate this as you normally would. This is 4x minus x squared over 2. Well, you could have added these two together or whatever. Again, nothing happens at x equals 0, so we just have to evaluate at x equals 2 and see what we get. So you get a minus 2 minus 1. That's, yes. And so you get 5. And now, so again, this is the computation of the volume using this perspective where you're sweeping out the region using vertical arrows. Now, there's another interpretation, which is one where you actually use dA as dxdy. So let's do that now. So now let's do horizontal segments first. So that means that you're going to take the A to mean dx dy. So notice that I have flipped the order, okay? So again, what are the practical consequences of this? So let me draw this region one more time here. Here you have 0, 2, here you have 0, 1. And now you're using horizontal arrows. Okay. And so again, when you do this business of computing double integrals, you never do anything to the function itself. The function is just what it is. So regardless of the order of integration, you put 4 minus x minus y again. And now, again, the idea is that we're flipping this around, so you have to write dx dy. And one more time, you read this from the inside to the outside. So the first variable of integration that you meet is the x. So let me just put it here. And so the bounds that you have to put on this first integral are the bounds for x, and x can go from 0 to 2. Right, so notice that x are the values this segment is only changing its x coordinate, right? And so the values of the x coordinates are changing from 0 to 2. And for the other one, the values of y, after you did this, now you start moving the segment, so you do like a sweep out, and so the values for y go from 0 to 1. And again, now what we do from this point of view is treat y as a constant. So this is like a partial integral with respect to x, so y is constant. And so let's try to do this integral. So you have to work the thing in the interior first. What does that give us? So you're integrating this with respect to x. 4 is like a number, it always is. So the integral of 4 with respect to x is just 4x. The integral of x with respect to x is minus x squared over 2, right? And now y is like a constant, so notice that the roles are in reverse. And so you put minus yx. And this you evaluate at x equals 0 and x equals 2. And finally, whatever you get is going to be integrated against y from 0 to 1. So this is the integral from 0 to 1. When you put x equals 2, you get 8 minus 1 minus 2y. You don't put anything at 0, right, because everything goes away. And so this you just integrate with respect to y. And again, this gives you 8y. Well, this is the same as 7y minus y squared y equals 0, y equals 1. Okay? And now we should get the same answer as before. And so I just need to check what I'm doing wrong. So, oh, good. When you square 2, you get 2 squared, which is 4 over 2. This is 2. So I'm sure someone would have pointed that out, but unfortunately, no one is here besides me. So you get 6y minus y squared, and now that's 5. Which is, notice, the same as we had here. So really, we computed the same volume, but in 2 different ways in this example. So I will do the same, apply the same process for a slightly more complicated case where you're looking at a triple integral, and you'll see that is basically the same idea. You just have to be more careful because there are more ways in which you can do like the partial integrals.